Okay, I might even miss something while trying to do this, but we will certainly try. So this is a screen mirror from my tablet. Okay, let's do this about elimination essentially, and as so we will talk about pivot now. So pivot is essentially a non-zero difference point. So we will get to it why it's non-zero, but due to elimination, to eliminate elements below the same column. So let's say we have this matrix, and this is the first pivot of that matrix. Cool. We see that. So it's simple to just multiply it with 3 and subtract from here. So because doing something like this does not change the solutions, we know this from the basics. I guess so. We did this here to found out that to found the new pivot. So this is the second pivot, because and this here. So we will do the same for this, and we have now the 3 pivots of a 3 by 3 column matrix, 3 by 3 square matrix, and which explains us the which essentially the multiplication of all these 3 pivots gives us the determinant. So which means nothing. This is just an observation about the determinant calculation. So how could this have failed if the pivot was 0? Obviously. So first thing is, pivot is defined as the non-zero difference point, so it can't be 0 once. But why it can't be 0? Because you can't multiply it and subtract from something to make the another thing 0. So obviously this can't actually be 0, or it should be a non-zero difference point. What we could have done is exchange the rows. So if the next pivot would have been 0, we could have exchanged the rows, because exchanging does not change the solutions. But now we have this matrix, this new matrix, and the corresponding change of the right hand side. Now we can form the equations with our variables. So this represents x, y, and z essentially, as we know from the basics. So we can just essentially do something like this, and now we can back substitute things. So this is a very basic thing. So back substitution here. So we know 5z equal to minus 10 from these, because these are essentially zeros. So we know that this is essentially equal to minus 10. So 5z is equal to minus 10. Now we can calculate z and back substitute here and calculate the other variables essentially. So this is cool now. Okay, for matrices, now let's talk about matrices. So say a matrix, a column multiplied by a matrix, post multiplied by matrix essentially means 1 times this column, 2 times this column, 3 times this column. So before, when I studied this in detail, I never noticed this, to be honest, with this level of intuition. But yeah, so this is how it works. So for this works same for the row matrix, but pre-multiplication. So pre-multiplication of row matrix means 1 times of the first row, second time 2 times of the second row, and so on. So okay, so what we were doing is essentially what we are doing with this. These 3 by 3 whatever this is not a matrix still, but we are doing row operations assuming these as variables. So we are just assuming x plus 2y plus z here, but that is but we can do the same using the matrices. If we know this basic logic, we can what we can do is use the old matrix. Let's say if I go a little back above, so see this matrix, to convert this matrix to this matrix, we just need another matrix. Which will be pre-multiplied by this, or maybe post-multiplied, we don't care about that, but which will be pre or post-multiplied by this to form this matrix. To convert this matrix to this matrix, we will call that an elimination matrix. So let's go here and see that for the matrices. So okay, so where the hell is this? Yeah, so what we need to do is subtract 3 times the row 1 from the row 2. So we need to multiply it with a matrix which can do something like this. So how can we build that matrix? For building a matrix, we need to keep this row the same and this row the same. So if we would what we would have done is just multiplied this, the above part, with this matrix. What we would have said is 1 times of this row, 0 times of this row, 0 times of this row's addition, which makes sense. We would only get this 1 2 1 but we need this same for this. So 0 of this, 1 of this. Got it here. For the second one, we need 1 of this minus 3 of this. So 1 of this, 0 of this, minus 3 of this. So this matrix essentially will be multiplied this to do the first step of the elimination. So this is the same slide explaining this. So one row of this, none of other rows, only 3 rows will retain the original nature. Cool. So this is the operation we are doing with that matrix. So it is called elementary or elimination matrix, which is e to 1. So why it is e to 1? Because it is used to fix this to 1 position. So this is the 2 1 position, and we essentially need to fix this position itself using the elimination. So we need to fix this position and make this 0. So this is called e to 1 matrix or elementary or elimination to 1 matrix. Cool. Okay, so there is some issue here, but okay. So we have to do the same. We have to do the same step on this matrix. The new matrix we calculated, where it is. So this, yeah. So the new matrix we calculated is this, and we need to do the same step and multiply it with some matrix. This time, let's say e32 to fix the third 32 position. So we need to multiply it with e32 matrix, and then convert this matrix to the next elimination step. Okay, so we'll do the same. So what we need to do is, if we go here and watch the intuition, we need to multiply this row with 2 and subtract this from 1 and make keep these two rows the same. So if we keep these two rows the same, we will have 0. Oh, sorry, wait a second. So we will have 1 0 0, which means for 1 of the first row, 0 of all the second rows. Then we also have to keep this row the same, and then we need to change the third row. So we need to keep the 1 of the third row, minus 2 of the second row, and 0 of the first row. This will form our matrix. This one. This is our matrix, which will be used to do this, and this is e32 essentially, this matrix. So what we did is finally multiply two matrices with A to form the final matrix U. So A multiplied by e21 and e32 will be multiplied with A to form U. Single matrix to eliminate. So the single matrix to eliminate would be this matrix e32, e21 with multiplied with each other will form a single matrix, which we can essentially use to essentially make a singular elimination matrix, which can be multiplied with A to give us U. Cool. So let's talk about permutation matrices now. Let's say, so the binary square matrix obtained by rearranging the rows of and columns of an identity matrix. Okay, so this is interesting. So permutation matrix is essentially contains the same elements, almost okay, the binary elements basically 1 or 0, and this is essentially used to change the or exchange the rows or columns accordingly. So each row and column should contain 1 as an entry. So at least each row and column should contain 1 as an entry. We will get to the intuition why, but yeah. So this is a permutation matrix. Pre-multiplication will result in change in rows, and post-multiplication will result in change in columns. How? So we also discussed the same exact thing here when we talked about matrices. So this permutation, we will create a permutation matrix essentially, but okay, sorry. Post multiplication will result in change in columns, so this will work with columns, and same with the rows. Okay, and we'll get to it in another intuition. So pre-multiplication will result in change in rows. Okay, done. So see, this is a matrix, this is a post multiplication, pre-multiplication matrix, so this will work with rows first. So we need 0 of this rows and 1 of this rows here at this position. So we have CD. If we do the same here, we have 0 of this row and 1 of this row, which essentially exchange the rows. If we do the same for this, so we have this with this, so basically 0 of this rows and 1 of this rows, and 1 of this rows and 0 of this rows, which essentially exchanges the matrix column wise. Basically column exchanges the columns. Inverses. So A inverse A equal to I equal to A inverse A. We know that if exists, A is multiple or non-singular. We know that. This is essentially the basic proof in 12th standard or maybe 11th standard, but if the determinant is not equal to 0, this will then be invertible, and A into B if is I, where B is the inverse of A essentially, and if we take determinant of both sides, this will be 1, and this should not be 0. If this is 0, this can't be 1 essentially anytime, so we can't exist. A is 1 3 2 6, and A multiply X is 0. If to do something like this, to make a null space, which we will discuss later, making a null space essentially. So okay, so while making a null space, we need to make this 0 if we say so. We need 3 of these columns and negative 1 of this column, which will result in 0. Now let's multiply by A inverse. So this is also a proof of this, but a better way to do something like this. So to make this 0, to make this matrix 0, we need to multiply this with the sum matrix. So if we can do something to multiply this matrix, let's say this column, so 3 of this and negative 1 of this will result this in 0. Now let's multiply this with A inverse. So the equation sustains, but if I multiply it with A inverse here and A inverse here in as a pre-increment, this will result in 0. But because the A inverse into A is defined as I, so I into some matrix X is 0. So X essentially has to be 0. It has no path to not be 0, but this essentially is not 0. We have 3 or minus 1, which does the same thing for us. This is not 0. Okay, finding inverse columns or vectors are pointing at different directions, hence the determinant won't be 0. We know that. So this is we can know this intuitively that 1 2 3 7 no, 4 1 2 3 7 these vectors are pointing at very different directions. If we see this, not very different essentially, but so if 1 and 2 is pointing here, 2 1 2 and 3 and 6 is also pointing here essentially. So this will always be 0 because there will be some combination of this which will make this 0. Okay, but if we have 1 2 here and 3 6 here, does not make sense. Cool. If we have 1 2 here and 3 7 here, something like that, now there is no combination of this or linear combination of this which will result with the result them in 0, the multiplication of them in 0. So not multiplication but a linear combination will never result in 0 in this case essentially. Okay, I don't know. Cool. So we can tell them apart for small matrices, even for large matrices I guess, are pointing at a different direction, so the determinant won't be 0. So if we know that this has an inverse first of all, or we can just calculate the determinant. So 7 minus 6 is 1, which is not 0, so this works. See, so there is an A inverse matrix. A into column J of A inverse will return column J of I. We know that. So we know that this column into this matrix will result in this column essentially. We know that. So equivalent of solving two systems. So basically this is essentially equivalent of solving two systems. We can simply solve these two systems to calculate A, B, C, D. But the bad thing about this is you need to solve two equations. We will do this in one. So Jordan made a method to do this in one. So we have an augmented matrix essentially here. So this is an augmented matrix, and here is our original matrix, and here is I. We will do some kind of operations with this method so that we will convert the I into A inverse and A into I, and we will see why this works actually. So this is the augmented matrix, and what we'll do is row elimination. So if we try to do row elimination, this is the pivot, and we will if we subtract this, we will get this essentially, which is simple enough. But we will not stop here because we need to make this matrix as I. We will multiply this with 3 and subtract from here. So we'll do the same for here, and this will become I. This will become essentially A inverse, but why? AI converted to I A inverse. So the A inverse is this. Okay, so why it happened? Let's see. So to convert the A, or basically this, to something, we would have multiplied it with some kind of elimination matrix. We did two eliminations, so basically E1 and E2, which essentially makes one fat elimination matrix. Okay, this is converting this matrix which we are multiplying with A and I is essentially converting this position to I. We 100% know this. So so we multiply this somehow that this will make A. We know that. So if A into I forms I, which means E into I forms I, we know that E is essentially A's inverse. So for E into I for some X matrix, okay, we don't even have to do anything, because let's say E into I for some X matrix, E is X matrix, isn't it? Obviously, because E into I forms some X matrix, na? So I has no significance. So E is X matrix, which comes here. So basically, here it is also E, but E is essentially inverse. So this is A inverse. That's it. Simple. Okay, so we have factorization into LU decomposition. Let's talk about the factorization into LU decomposition. Yeah, so now what we were doing is multiplying a matrix with E to form a U matrix. Now we are trying to do is split A into L and U. So AB. Okay, so this is basic law of inverses. I guess everyone knows that AB multiplied by B inverse A inverse forms A. So this also works for the transpose essentially, because uh, this also works for the transpose essentially, because we have to do that. Obviously we have to do reverse the steps now. So if we have a into b, to reverse this, so we had I is initially multiplied with multiplied it with a and multiplied it with b. This formed ab. We started from I, we formed ab by multiplying by a and b. We need to reverse steps manually as we did. So reversal would be done from the last. Obviously we can't, if you are just making a stack, we made a book at the bottom, second book at the top. To reverse the steps, we need to first pick the second book from the top. So this is the same logic here. So this is an let's see what we are doing here. So this is some A matrix. We need to split A into LU. Let's keep that objective in mind. So let's see what we are doing here, and we will understand the intuition later. So we have A. We will multiply A with e to 1 to eliminate this and fix this as to 1 position. We will get a U. This is what we were doing. Okay, we will capture this e to 1 matrix and save this somewhere. So we have A, we have U, but because A is L inverse U, because if we multiply e to 1 inverse here, we will get A equal to e to 1 inverse U. So basically this part is e to 1 inverse. Cool. So we have e to 1 captured with us. In this case, L is essentially e inverse or e to 1 inverse, or we essentially know this. So what is just happening is this matrix is equal to U matrix, the same matrix, and the inverse of this matrix. The inverse of this matrix can also be calculated intuitively. We don't have to apply another Gauss-Jordan on this to find the inverse, or some other solving this by two equations. But see, this is taking four columns away. We can bring or add 4 columns into this, so to make the inverse. This is what this matrix is doing, keeping everything same but taking away those 4 columns from whatever we are multiplying. But here we are studying that's it is as simple as that. So this is the inverse of this, this is this. So basically we split this into 2 matrices. This is the inverse using the inverses, the capability of inverses that we know. Okay, so further factorized. So this can be further factorized. Sorry, not this, but this can be further factorized to make this more balanced, because this is upper triangular, this is lower triangular. This is not actually important, but we can do this something like this to do something like this. This is not a very something crazy shit. Okay, for 3 by 3 matrices, so we need 3 matrices to that would be multiplied with that to make it U. So with no row exchanges, we are considering no row exchanges. So A would be inverse of this, into inverse of this. We have to do 3 inverse multiplications of the elimination matrix to find the L of the LU decomposition. So this essentially means while we are calculating the elimination matrices, let's say if we are doing this in program or replicating this in program, we are calculating these 3 inverse matrices and storing them in the respective positions or somewhere in the memory, so that we can come back to them later, inverse them again, multiply them to find the decomposition of A into LU. Okay, so let's say, okay, what is being taught. So these are E31, E21 and E31 matrices which can be calculated. So we assumed these matrices, let's say we just assumed these matrices, and we assumed E31 as well I. So multiplication of these 3 matrices which we assumed, this forms a new E which is left of A. So at the left of A we have this E which is multiplication of these 3. So we have to inverse them in reverse order. So I has no significance, so this will go here, this will go here, and we know if we are taking 5 away, it is adding 5. If taking 5 away, we are adding 5. So this is the inverse, this is the inverse, and we are inversing them in inverse order because of the stack example I gave. So simple. So what I was saying is, so yeah, so this is the multiplication which gives us the actual L. So A is LU, which is at the left of U essentially. How expensive is this elimination? So this was fine, but how expensive is elimination to the processor or something like this? Yeah, so this is a little intuitive. This you can't find the exact operation of how expensive it is, but we can just calculate a rough estimate of how expensive it is. So okay, so let's say n is 100. So this is a 100 by 100 matrix essentially. So we will have to multiply and subtract. We know that whatever when we are doing the elimination steps, we are multiplying and subtracting. So for each step of elimination, what we are doing is, for the, let's say for the first step what we are doing is subtracting from here, subtracting this row from here. So we are subtracting, we are changing each element except the first row. So it's a 100 by 100 matrix, so we are changing each element except the first row. So yeah, these all the elements are being changed, so each element will require one operation. So if so, this would be approximately equal to 100 square minus 100. So basically it will be 100 square minus 100 if we go precise, but it is approximately equal to 100 square. When we are at second step, because all of these elements are 0, and now we are only applying operations to these 99 square elements for the second elimination step. So this is the 99 square element. So similarly we will do this till we go to 1, and we will find this series, and we know that the summation of the series is this. To make a rough estimate, if we push into a very large number, this 1 will become insignificant in front of it, so we can just remove this 1 and this 1, and we will find that this is roughly equal to n cube by 3. So we will have to perform a rough amount of calculation if we want to do it. N cube by 3. And for the right hand side, it is obviously n square elements. So yeah, so this is a recitation from the lecture. This is a problem of LU decomposition and how it will be applied in real problems. So this is a recitation problem. This is simple enough. So this is a matrix with both numbers and some variables with A and B. So we need to calculate when it exists, and when for the LU decomposition, when for all the real numbers A and B, when it doesn't exist. So this is the matrix. We'll multiply it with such a matrix. So let's see. This is a matrix, and we need to eliminate this. So we need A times this and 1 times this for this row. So 1 minus A, 0 will be second row, and we know the first. Okay, we know the first and second rows essentially. So see, and similarly for this row, because there is no 0 here also, we need to multiply this with minus B and plus 1 of this. So this is essentially the same. So E1, we need to store this E1, and we will get this. We'll apply the same operations and find the E2, and we will make this matrix with 3 pivots. Cool. We will get a U matrix at the end, but we also get E1 and E2 and E3, 3 matrices. So here they are. Okay, so here we started. Wait a second. So yeah, so essentially we have these 2 matrices only, but to show the 3 steps or the 3 pivots we are designing, we can just split this into 2 parts, like this A and B, and for minus A we have plus B, for minus B we have plus B. Because of the inverses, we will multiply these 3 inverses, and because this is so easy, you can intuitively multiply them. So this will be clubbed together essentially. So this will be clubbed together, and we have 1 AP, and this is the matrix, which is essentially L, which is found after the LU decomposition which we did. Then we have permutations and the vector spaces. So this is interesting, and the vector spaces, and here is the actual algebra which is starting. Okay, these were just prerequisites. Let's talk about the real algebra, real linear algebra with the permutations. So we know that permutation matrix is used to execute row or column changes. So to avoid any 0 pivots, we need a P matrix by the side. We gotta know this. So because permutation matrix is essentially used as a method to exchange the rows, but if while doing the elimination, while doing the decomposition, we are doing essentially the elimination, but while doing the elimination, if we need a row exchange, we essentially need a P matrix. But in this case, which we did, which there were no row exchanges, this is essentially the I matrix. So I matrix is also a permutation matrix, but it does not do any row exchanges. That is okay. So we have now the vector spaces. The font is the thickness is changed. Vector spaces examples is R square. Okay, so we will understand this in some time intuitively, but all the 2-dimensional real spaces comes in R square. So XY plane, any vector in XY plane is the part of R square. So R square consists of all the so R square consists of all the vectors in 2-dimensional space. Okay, so 2-dimensional real space, XY plane. Cool. So these are all the columns. This will always exist in XY plane. So these are part of R square. What is R square? R square is a space consisting of all the combinations of R square. So the 3 here we have 3 2. Here is a 3 2, and if we want to locate let's say 6 4, we have to just multiply it by 2. So every single combination of this will be present in its space, which is R square, if this is in R square. We know that. So if some vector is in some space, and its combination will always be present in this space if this is the part of the space. That's okay. So R cube, all the real vectors with 3 components. Simple. So every single real vector with will be, okay, let me add some charging. Cool. So yeah, so R3 all real vectors with 3 components. Cool. Not a right vector space. Let's understand what is not a right vector space. So see, this is a vector space. We know that this is a R2 vector space. Every single vector of 2 dimension exists in this xy plane. Cool, we know this. But let's say we just remove every part in these 3 quadrants and leave this quadrant alone. This is 1/4 of the quadrant. Okay, we know that. So only positive numbers, let's say. So we have some vector 3, 2 exist in this space, but linear combination of this vector or scalar product of this vector. So scalar product by any number or linear combination of these vectors. So let's say we have this space only this part here. So this vector here, we have this vector, we have this vector. Both are in the space. Combination of these 2 vectors or the linear combination of these 2 vectors also exist in the space, but the scalar product will not exist in the space always, because this, we have this vector multiplication with -1, which is a scalar multiplication with this vector, will exist here. This vector does not exist in the space. So yeah, so let's say we have this vector. Yeah, so this is simple. So if we multiply this 2, this will exist. This will be the metric of a vector, but this does not exist in the space. So this is the condition of some space to be actual space, or some combination of vectors to be actual space, if a linear combination or scalar multiplication of any of the vector in that space, or the assumed space or apparent space, not apparent actually, but the space, any vector in the space, any scalar combination or linear combination should also exist in that space. Can you add these 2 vectors safely? Yes, but the problem is multiplying with scalars, not in the space. It's not under it's not closed under multiplication. That is the terms we use essentially, that it is not closed under multiplication. So the apparent thing is the vector space should be closed under linear combination of all sorts. So basically, if we have this vector AB, and okay, if we have this vector AB, we have this vector CD, and we are claiming that these 2 vectors exist in a space, this should also be true. Let's say L. So this should also be true. So any linear combination of this with multiplied by K multiplied with L and summation or subtraction of these, the vector resultant vector should also exist and in that space, for the space to be claimed as a real space or as a space. So what if the part of R2, what is that the part of R2 but is still a closed space in itself? Okay, so we need to now find this interesting thing, that what is the part of R2 but is still in the closed space itself, which means we have a bigger subspace, a bigger space. I've just revealed that it is a subspace, but if we have very big space, not very big space, let's say not space, which is R2 essentially, and R2 is an xy plane or xz plane or some yz plane. So we have a space, R2 space, and what is that? The closed space in itself, which is also the part of R2 but is still a closed space in itself. Okay, well, let's assume this line, let's assume. So any vector on this line, any one vector on this line, we have one vector on this line, we have another vector on this line, the summation of these vectors lies here, it will lie on this line. Okay, we have this vector, we multiply it with 2, it will still lie on this vector, this line basically. Okay, so linear combinations of any sorts on any vector on this line still exists on this line. So this is essentially a subspace of R2. Let's say this line. Okay, multiply by scalars, vectors, then okay, we got here. So E2, another subspace. Let's say if this is another subspace. So this is a line same as this line but shifted with an offset, some offset. So here we have one vector, second vector. The summation of these vectors lies somewhere here. This does not lie on the same line. Cool. This is one vector. Double this vector also lies on this line. Now does not lie on this line. Okay. Let's multiply this with 0. this vector lies on this line. If you multiply it with 0, it lies here. So we get that this is not a subspace or a space in itself, or a closed space which is the part of the bigger space in itself, or a subspace. We will obviously call this a subspace. So for a closed space to be a subspace of R2, it must pass through 0 vector. We know that because we are allowed to multiply any vector by 0, and the resultant should also lie on the line, which means the multiplication with 0, which we can anyways do, will lie on which will be equal to 0. So the line should be passing from the 0 itself. We multiply this to 0. I'm at origin. I'm not at that line anyways. Okay, so subspaces of R square. All of R square is obviously the subspace of R square. Obviously, any line through 0 0 will be the subspace of R square, and 0 vector in itself is a subspace, because 0 vector at 0 vector we have only the 0 vector. So 0 vector plus 0 vector will always be 0 vector. 0 vector multiplied by some scalar will always be 0 vector. It also satisfies the conditions of subspace, so it's a complete subspace in itself, although it only has one element. So we have 3 subspaces in R square. Similarly, we have 4 subspaces in R cube. We have all of R cube, any plane passing through 0, any line passing through 0, 0 vector only. Cool. 1 2. Okay, so this 1 2. We have an A, essentially columns in R cube. So we have columns in R cube, all of their combinations form a subspace called column space. This is a very interesting thing from the intuition we just received. Okay, so this is kind of interesting because any combination of this vectors, these are 2 vectors in R3 essentially, any combination of these 2 vectors, okay, leave it any combination. So if we combine these 2 vectors, we will add them to a space. So let's say we have a bucket, and what we will do is take every single combination of this matrix. So let's say we have 0 times this, 1 times this. This will give us a result, a linear combination. We will put that into a bucket. Okay, we will take 1 times this, 0 times this. This will also give us a linear combination. We'll put that into a bucket. 2 times this, 3 times this. We will put that into linear bucket in a bucket, and this will, after we get the space. So every single combination which can be possible will be stored into that bucket, and that bucket is itself called a column space. So we got this columns in R3, all their combinations form a subspace called CA. Cool. So which is columns essentially. So this is column 1, column 2. So essentially this is column 1 and column 2. Because this lies in R3, every single combination of these 2 columns will essentially form R3. How do we draw the whole column space? All the combination of these 2 vectors in R3. This makes a plane. See? So how this makes a plane? This will make some plane like this. Because these are only 2 vectors in R3. So we know that to calculate a plane, or let's say to calculate a plane, we at least need 2 vectors, or we at least need 2 vectors, a point from which 2 vectors are passing, and a normal vector which can be calculated using these 2 vectors. So which makes the 2 vectors. So see, this is very simple or intuitive thing. So let's make a plane first. We have these 2 vectors, every single of because this is ever expanding outside, so any combination or linear combination will lie in this dimension. This will never go up in the 3rd dimension, which essentially makes this a plane. But if we had 3 vectors in that column, in this column space, it will essentially form an R3. So because considering if any of 2 are not in the same plane, but all 3 are, at least 2, only 2 are in the same plane, and another 3 is in different plane with respect to each other or mutually. So we have these 2 vectors and 3rd vector here. So this will essentially consume the whole R3. We can also see we only have 4 of the subspaces. So it can't be in 0, it can't be in a line obviously, so it should be in the plane. So then just the next one. Okay, how do we draw the whole column space? Okay, we've done this. Okay, summary: the condition for a set to be linear space, take 2 elements from the set any set to be in a linear space, take two elements of a set, take the sum of those sum of them, and then they should also be in the same set. Take any multiple from the set, the element should be in the same set. And in a linear space, if you find a subset which also satisfies the two conditions, then that will be in that subset. So we have a recitation problem: x1, x2, find v1 subspace generated by x1, v2 subspace generated by x2. Okay, and describe v1. Okay, so basically we have x1 subspace generated by x1 is v1. So v1 is this line essentially, which is the extended version of x1. We know this essentially. Same for v2, but the summation of the subspaces only contains the zero vector. So we have this subspace of x1, ever expanding line, this line. The only point of intersection is this 0. So the zero subspace is the intersection of these two subspaces of R3. Okay, x1 x2 together. Okay, this is the so for x1 and x2 together, this will form a plane. We know that this will essentially form a plane because the scalar multiples of these two will be in a plane. To get v3, we need a full plane to satisfy the addition condition. Okay, this is simple shit. Okay, we won't go to that. So we have lecture 6. We know that. No two requirements of a vector space now. Okay, okay, P and U, all vectors in P or L. This is not a subspace. All vectors in both P and L. This is a subspace. See, we gotta understand this intuition, because all vectors in P or L might not form a subspace essentially. If P and L are two subspaces, but the intersection of that will always be a subspace. We all saw that example here, that this is a subspace in itself, this is a subspace in itself, but the summation of these two subspaces, or the union of these two subspaces, will not form a subspace, or will never form a will not form a subspace essentially, because the intersection is the 0th point, and this will form a subspace. Because this will never form a subspace, because this vector and this vector, the summation of this will not lie either on this, not on this. So the summation of this and this will lie somewhere here. It is not in either this space or this subspace, which is if we are talking about the union, but intersection is 0 vector here, so it will always lie on the subspace. So this is the point to be noted, that the intersection will always provide intersection of two subspaces will always provide a subspace, but not the other way for the union. Generally, for subspaces S and T, the intersection is a subspace. Yes, we just talked about this. Column space of A is the subspace of R4 in 4×3, because we have 4 dimensions now. Let's assume these are some 4 dimensions, and we have 3 vectors in that. So similarly, if we have 2 vectors, this will form a plane, which is R2 in itself. 2 vectors in 3 dimensions. So if we had this kind of matrix, we would have 2 vectors which will form a plane as a subspace. Here we will have a 3-dimensional body, which is R3 as a subspace. So the column space is R3 in R4. Does Ax B will always have a solution to every B? No, because it has 4 equations but 3 unknowns. We know that it has 4 equations but 3 unknowns. So there will always be something which will resist the solution. It will always not give the solution, because these can be parallel, and we will have, let's say, 2 parallel lines. So there will be no solution, or intersection lines can have infinite solutions or a single solution or whatever, but this is not the case, that we will always have something like this. So this is the situation here. For some RHS, we can solve this. Let's say B equal to 1, 2, 3, 4. So for B equal to 1, 2, 3, 4, we can solve this. Not B, so sorry, this not X, for B equal to 1, 2, 3, 4, we can solve this, because we can put 1 of this column, 0 of this column, 0 of this column in here, see here. Then for X equal to 1, 0, B 1, 1, 1, 1 is also okay. Same, because this is the column here, so we can put 0, 1, 0. We can solve X equal to B when B is exactly a vector, the column space CA. We can solve X equal to B when B is exactly a vector, column space of CA. So B should be at the column space of C. See, it is very intuitive thing. I might have spoke intuitive 15 times or 30 times in a row, but see, if this will be solvable if by multiplying this matrix with this matrix, because we see it is simply the combinations of these two vectors. So if B would have been 3, 5, 7 and 9. It would have been solvable because this will be 1, 0, 1. So one of this will result in this, which essentially means for linear combinations of this, which the linear combinations will be created by this matrix here, there will be existing B. So we can solve this when exactly a vector space. So the linear combinations, what are linear combinations of all the columns? It is a column space essentially. So basically, for some vector to be in the column space, basically for some vector to be has to be in the column space, so this vector has to be in the column space of this to exist. Simple as that. Or when B is the combination of columns. Okay, exactly. So this is the line which is defining this. So when B is the combination of columns is column space. Can we throw any column through? Okay, can we throw any column and still get the same vector space? So see in this, can we throw any column and still get the vector space? 100%, because the summation of these two columns is resulting this. So what we can do is throw this column away, and using the combinations of these two, because combination of these two is this, so with combinations of these two we can still get the vector space, column space, which you are getting using these three vectors. So let's say I remove this vector here, I will still get the same column space, because the subtraction from this will result in this. So this is useless with respect to these two, this is useless with respect to these two. That's how it works. So we can still get it's the same column space with two columns. This column is summation of 1 and 2, hence we won't change anything from the column space. We got this. So we call these two columns as pivot, and this column as dependent, because this column is essentially dependent on these columns, which we are calling pivot columns. So we can also throw column 1 if you think about it. Okay, we already talked about this. So null space of A. Now we have already talked about the column space. Now we can proceed to talk about the null space of A. Ax equal to 0. Last time we were calculating Ax equal to B, but now we have to calculate Ax equal to 0. Ax equal to 0. So we need some vector which will multiply this and give us 0. So 1 is 0, 0, 0 obviously, but 1 is okay, this is okay. So 1 is 1 of this, and minus 1 of this, because the summation of these two is results in this. So we can add these two, subtract this one, and still get this. Okay, there can be a lot of vectors with respect to this one if we multiply it with the scalar. Hence the whole null space can be summarized in the following vector. Yes, exactly. So that's what we talked about. So C of 1 of 1 minus 1, and scalar here can result in this. So this is essentially a subspace, because C can also be 0. So this is the line which is 1, 1, minus 1, which is a subspace, and a subspace is a null space. So subspace is closed in itself. Null space is, to be a space, it has to be closed in itself. So null space is a line in R3. This is also a line in R3. Okay. Simple check that solutions to Ax0 will always give a subspace X. If Ax equal to 0 and Ax star is equal to 0, then Ax plus X star is also 0, and X plus X star will result in Cx. Not result in Cx, but C, essentially C. X can have multiple values. X can have X, X can have X star. So summation of these, we can take a common and still have the same 0. And obviously Cx we can multiply C in both sides and still have 0. Is this a vector subspace? Let's see. Let's move on here, and let's talk about the here. So this is a vector subspace. So we know that to determine a vector subspace, we have already calculated the column space or the null space. To determine a vector space, the first condition was it should pass through 0 vector. It ain't passing through 0 vector, by the way. Let's see if it is. Can't remember where it was. So okay, let's find where it was. So you've done this, done all of this. Yeah, so see, this is not passing through obviously the 0 vector here. So this is not a vector subspace, though we have a column subspace which will exist for every column essentially, and a null space which is minus 1, 1, minus 1, plus 1, plus 1, minus 1. Yep. So computing the null space, let's examine how we can compute the null space essentially. So this is our normal A vector applying elimination. While doing elimination, we are not changing the null space. obviously, because while doing this is obvious. So if we are doing computations or linear computations, we can't change the null space because we are essentially multiplying it with some value, adding or subtracting. It also already exists in the null space, no? So we're not doing anything there. So elementary 2 operations does not alter the solution, obviously, we know that. So yeah, that was the term I'm finding, elementary 2 operations. First pivot, we will subtract that, we will find the second pivot, and then we will have to do a row exchange. Zeros can't even perform a row exchange. Okay, shit, because they are all zeros, we can't even perform a row exchange. It will not benefit anything, but this is whatever we can do. So we found 2 pivots and form this matrix. So because this is an echelon, an echelon means a position, so this is essentially means a position. So this is exactly like a stair or a position, stairs in the podium of first or second. You got that, no? So this is essential form, echelon form, and this only includes 2 pivots. So we have this pivot and this pivot. So essentially the rank of A is number of pivots of the matrix. So if we have to define rank of any matrix, which is just a term to represent the number of pivots, we have rank. So these we will call these 2 columns as pivot columns and these 2 columns as row columns. Cool. We can assign any value to variable 2, 4 and solve for 1, 3. This is kind of obvious because these are free, they have no pivot or no reference points. We can assign any value to them and solve for 1 and 3. So this column of 4, this column, we have to provide some values to these and we can do anything with them. Okay, so we can assign, okay, so let's see, freely chosen values. So the freely chosen values will be, let's say we chose 1 over 0 or 0 over 1, minus 2 of the first column and 1 of the first column, minus 2 of the first column and 0 of the third column will essentially result in a null matrix. If we chose this matrix, let's say we will build a matrix here, start building matrix here, we can choose this one and this one freely. We chose 1 or 0, and now this is 0, sorry, this is 0, this is 0, because this is 1, this is 0, and we need something to make this 0 essentially. So we have minus 2 of this one and 0 of this one, because we have 1 of this one. So okay, already, so we have 1 of this one already, minus 2 of this one and 0 of this one, 0 of this one. So this will form a matrix essentially if we see of it. So minus 2 of the first column, see, same thing. Now choose the free variables 0, 1. So first we chose 1, 0 and we will now choose 0, 1. There is a reason behind this, we will talk that in some time. So after choosing 0, 1, we will find the vector like this. So we know that we can multiply this with some scalar value, because multiplying with a scalar value will still give the same null space, and same with this. So the null space is a linear combination of these 2 lines generated by choosing 2 variables or 2 free variables 0 and 1. Cool. So any linear combination of these 2 will generate the whole null space. Okay, more rational method or more computational method. So we have this, we know that because we only have 2 pivots. Represent pivot variables in the form of free variables. So we can represent the pivot variables in form of free variables. We can calculate the value of these in terms of these, and then we can put this in a matrix. So we have x2, x4 and these 2. Okay, now we can split these 2 matrices like this. So while doing this, we already saw we got the free variables which we chose here as 0, 1 and 1, 0. So this is a simple method which will include the whole null space if we use these free variables exactly. But if you choose any free variable here, let's say 1, 1, and then compute for these, you will also get the vector you will get will also be in the null space. That's for sure. So the row zeros appeared because it is the sum of 1 and 2, and the elimination discovered that fact, and that is the most powerful thing. So this essentially means because we already concluded that in the matrix where it is. So let's see here. So this is sum of these 2. This is the sum of these 2. We know that. So to calculate the null space, we could have removed this because this is essentially the dependent row. Now this is essentially the dependent row. These are independent rows. So this became 0 after elimination because this is the combination of these 2, and we discovered that fact using the elimination, and that is kinda crazy, bro. Okay, so now we can if we have the echelon form, we can now create the calculate the row reduced row echelon form. Has 0 above, below pivots. Okay, so it has 0 above and below the pivots, so this should be 0, this should be 0 essentially. So we can just simply perform another elimination step and multiply or directly subtract, multiply some matrix with this, which will essentially subtract this row one times of this row from this row, and we will get this. We can also make all the pivots 1. We can make the pivots uniform by dividing this column with 1, this column with 2, and we will get something like this. So this is a RREF, a row reduced echelon form. So we can notice this as I matrix, and this has some another matrix F. If we look closely, if we just exchange the columns, because columns exchanging does not dissolve the spaces or something like that, so we can just see this is a redundant row. By doing some exchanges, we can find this is I and this is some as another vector F, sitting in pivot rows and columns back substitution with F. Simple shit. Okay, so we got the null space, and if we see this F vector, which is 2 0 minus 2 2, is just the opposite of this 2 2 0 minus 2. From this, if we notice that so these are pivot columns, these are free columns. We also named it as named this as F. These numbers are apparently reversed. See, these numbers are apparently reversed. Minus 2 minus 2 2 2 2 minus 2. Explanation is the RRF form, about the RF form, this form, why it is reversing. So there are R pivot columns, we know that, and n minus r free columns. R is the rank, so there are pivot columns obviously, and n minus r is free columns. So this is the R row reduced echelon form, and we will multiply it with some null matrix, and we will get 0. We know that. So the null matrix will always be minus f and I, because if this R is IF00, we will multiply this with minus f and I to expect a 0 matrix. So we can see why the null space see, this is crazy, not crazy, but see, this is kinda, this should be intuitive, but we found it with some calculations. But because R is a form of A, we just multiplied or divided or did some row operations. It does not change anything, or does not takes away anything from A. If we take any matrix of the null space would be minus f and I for this matrix, and which means this is essentially reversed. So that's why we saw these reversed. Computing null space of A transpose. This is fairly simple. This is the same process. So we just transposed the A, did same thing for this. So here we performed a row exchange, by the way, because multiplied by this 2, this formed a whole 0 row. We exchanged this row, so we got this row now. We got the second pivot here, and then we did the same thing. We got these 2 as 0, rank 2, and rank of A and A transpose is same, and we discovered that fact just now. Okay, we have 2 free columns, 2 pivot columns, 1 free column. So we have the null space. This is the null space. This is the null space, because we can take 1 here, and that's it, because we have only one free choice. Essentially what we are doing here to calculate the null space is, let's say we have 4 free variables, free columns. We will take 1 for one column and 0 for all, then 1 for one column, 0 for all, and we will repeat the same for everyone, just like this. So we only have 1 column, so we will take 1 and 0 for none. So that's it, I guess. So this is the null space for this one. We can simply calculate the RREF, and we will achieve I here and F here. That's it. And for the null matrix, we have minus f and I, minus f and I. Lecture 8. So I guess we were calculating null spaces till now. Now we'll be calculating Ax equal to B using the same methodology we got. So we have some sort of linear equations. We have this augmented matrix here, simple, built from this. We know that B3 equal to B2 plus B1. We can see this. Why? Because summation of these two forms this matrix, and elimination should verify this, just like before. Elimination should verify this. We did the elimination. Obviously we got 0. We got 2 pivot columns. We should have gotten 0, obviously, because the summation is okay. We got this. So this is the augmented matrix, this on the right side, and this is equal to 0, and B2 plus B1 equal to B3. We again verified this. Okay, so let's assume B to be 1, 5 and 6, and we have to assume something which adds where we add B1 and B2 and get B3. So we assumed 1 by 5 3, and for 1 5 3 for B1 B2 B3, after elimination the right hand side of the augmented matrix would become 1 3 0. This has to obviously become 0. So let's see the solvability condition for on B. So Ax equal to B, B is solvable when B is C. B is in CA. Okay, let's understand this again. So this will be solvable when B is in CA. So what is CA? C is CA, column space of A is combination of all the columns, combination of all the columns and making a space. That's it. And B should be in that because this should verify this. And for verifying this, this should verify the elimination, and for elimination verification, this should add from a linear combination and result in 0. So this should be verified this by this, because this is essentially equal to this. Got my point? So means B has to be combination of columns. Simple. If a combination of rows of A gives 0, so the same combination of entries of B should give 0. If a combination of rows of A gives the 0th row, the combination of entries of B should give 0. Simple. To find complete solution of Ax equal to B, let's see. So we need to first to find the complete solution, we first need to find Ax equal to B, or a particular solution. For the Ax equal to B, we need to find the first we need to find the particular solution. Set all free variables to 0, and then solve Ax equal to B for pivot variables. So X particular calculation will go something like this. So we need to first find a particular solution. We can find that by substituting all the free variables as 0. So x2 and x4 are 0 here. And now we can evaluate x1 and x3, and then we can find x particular. Now to make this a space, we can add a null space to it. And see, adding null space won't result in change of anything, because axp is B. Okay, that's very bad handwriting. Okay, axb is B, and axn is also 0. It's 0. So adding both will just make a new x which also satisfies B, Ax equal to B, because adding this in here, or the null space to this, will also result in a new x which will result in B, essentially, which will satisfy B. So this is the complete solution. This is the null space which we added to the particular solution, and this is a plane. This is a plane which is passing through this point also. This is a plane. We found that the null space is a plane for this case, essentially, and this should also pass to this point because this is satisfying this also. So that's it. For m and n matrix of rank r less than m and r less than n, for full rank column means r equal to n. So there is some specifications now. Let's go into this. So for full rank matrix 1 2 3 6 5 3 1 1 1, this is a full rank matrix, or for rows, full rank matrix for rows. So because there the r is 2 and the n is 2, so we will only have 0 or 1 solutions if B is a linear combination. B is a linear combination of these linear combinations of the columns. We know that it has to be. So it will only have 0 or 1 solution, because there are no free variables to build those solutions or more solutions. Okay, full column rank, it's same that r equal to m, and here the rank is 2, columns are 4, I guess. Okay, this is a full row rank and this is a full column rank. I've just reversed the names, unfortunately. So see, this is a full row rank essentially, and this will have 1 or infinite solutions. 1 is the part of the infinite category actually, but because there are 2 free variables, because the rank is 2, only 2 pivot columns, we can have infinite solutions, or we won't even have 1 solution. Anyways, we will always have infinite solutions as far as I know. Okay, so if we have the square matrix, we will have 0 or infinite solutions, and because if we have 1 solution, we will have the infinite ones. Okay, recitations to find the solutions of all depending on B1, B2, B3. Okay, cool. We will build the matrix, the augmented matrix, do our elimination steps, and for no solution to exist, this should not be equal to 0. We are getting that. Okay, that is simple. And we can then calculate the RIDF, pivot variables, the free variables, the F here, the I here. To find the particular solution, put free variables to 0. We got that. So we can find the free variable, and then we can calculate the null space, add them. So these are all the solutions of Ax equal to B. So Ax equal to B solutions are xp plus c of xs. Now we have the most significant thing, which is independence, and we will talk about this. So I guess we should now talk about independence, lecture 9. So this is kind of a little confusing. The lecture is essentially confusing at some point of time, but we will I believe we will get it through. So independence. So 3 vectors, or x1, x2, or x3, just 3 vectors, are independent if there are no combinations of them, that gives 0 vector. We know that from a lot of time, essentially. Okay, I will not try to find that, but we have columns, and we knew that if these two columns, the combination of these two columns result in this column, or the combination of these two rows will result in this row, there will be a null vector, and this will result to 0 somehow or anyhow. So these two vectors will be independent, but this will be dependent. So 3 vectors together will never be independent. But if these 3 vectors does not give the combination as zeros, that will not work out. We got that. Okay, so this is the equation. So if combination of any x amount of vectors does not give 0, then all the vectors are independent from each other. This is not even this will never work for independence, but linear combination 0, hence dependent. We know that. So if these are two vectors, the linear combination this will be dependent. These 3 vectors linear combinations. We take a matrix. This is the matrix, and let's assume values for v1, v2, and v3. They are 2-dimensional columns, essentially. Let's assume if this is true, and AC is 0, let's say. So for some c vectors, let's say it is 0 for once. There exists a vector which gives combinations of these columns as 0. How do we know that? Because we have a free variable. Okay, so this is interesting. We have a free variable in this matrix. When we do elimination, we will have a free variable here, or a free column here, which will result in a null space, essentially, a building of a null space, essentially. So we can directly view at a matrix, and say if it is independent or not. Certainly. So it is 5 by 2 minus 1. So we can simply say that let's make a something. So let's multiply this by 3, multiply this with minus 3. So if I multiply this with minus 3, okay, minus 3 plus 2, or if I multiply this with minus 3, which is 6 plus 1, okay, that's not too good. There will exist some null space, essentially. Some of this, and some of this will form something like that. Okay, so let's try to make one very quickly. So this should form this. So okay, so minus 3 of this, minus 1 of this, or let's say minus 1 of this directly, in plus 1 of this, and minus 1 of this, minus 1 of this, plus 1 of this. So we have 2 minus 1, already 1, and plus 1 of this also. So minus 1 of this, plus 1 of this, and plus 1 of this. Okay, this is not making the null space, but we get the idea that because we have a free variable, there will always exist a null space, because null space is made by the free variable itself. So we had that free variable, we built some null space like this. We'll see, because there was a free variable, and we put that free variable as 1. If we don't have a free variable, there will essentially be no null space, most probably, because we have a free variable. Okay. When v1, v2, vn are columns of A, they are independent if null space of A is a 0 vector. See, so the null space of A can only contain 0 vector, because the null space is essentially made for some of the unions of some spaces, which are these two, intersection of some spaces, and this should pass from 0, or unless, okay, because any vector or any matrix will be 0 if it is multiplied by these 3 0 vector or a 0 vector. So you can't deny that. So, but this will be independent because if there are no combinations forming 0 unless the 0 vector, they are dependent if AC is 0 for some non-zero C. Okay, so for rank equal to n, there will only be 0 0 0 satisfying this. So if I just remove this, there will only be 0 0 which will satisfy this. And for rank less than n, like this case, there is a free variable which will result in some null space, some kind of null space. And vectors v1, v2, and spanner space means, okay, let's try to calculate a simple null space for this. Okay, let's go here somewhere at the end, and let's paste this. So let's calculate some kind of null space for this. Let's calculate the first free and pivot variable. So I will multiply this with 1 by half, I guess. So add subtract this from here. So 2, 1, and 5 by 2. Multiply this with the half. So this is 0, half. If I multiply this with half, this is 3 by 2. Multiply this with half, which is 5 by 4, and minus 1 minus 4, so minus 9 by 4 essentially. And the next pivot is this. So these are the pivot columns, these are pivot columns, and this is the free column, and we can also make this 0 if we can, I guess. So we can subtract this from that. We can work around with that. So essentially we can get the null space somehow. Okay, shit. See, okay, so let's revise once for a second. How we calculated the null space for more clarity. Let's say it is not a null space calculation, this is a null space calculation. So this is as simple as that, to just reduce this to this form, or a row echelon form. So this is a row echelon form. So took the pivot, subtract, we got the second pivot, subtract, we made a whole row 0. Cool. And so that's how we found that the third row is the combination of first two rows. I'm not able to find that here, I guess. Okay, the example might not be absolutely correct, but okay, let's move on. This is where we were. Yeah, basis, independence. So we got the idea of independence, that there is a vector that gives combination of these two columns as 0, because we have a free variable essentially, and when v1, v2 and v3 are columns of A, we got this, everything is correct. So vectors v1 to vn span a space. So this is essentially a new term. So some vectors are spanning a space, which means the space consists of all the combination of those vectors. Okay, this sounds familiar when we talked about column spaces. So okay, so this sounds familiar when we talk about column spaces, because the column spaces are essentially the vectors of the column span a column space essentially. The spanning means that the space consists of a space from these vectors consists of all the combinations of those vectors. So this is exactly the same for the column space. So all the columns, the combination of all the columns are in the bucket of the column space. Take all the linear combinations and put them in a space, and that's spanning a space. Columns span the column space. Minimality, the space S is considered the smallest, space S which is being spanned is considered as the smallest, because it includes exactly what is needed to cover all the combinations of. There is nothing more, nothing less, but yeah, this is the smallest subspace we can create. If you were able to create a smaller subspace that does not include all the combinations, you were to create a smaller subspace that does not include all the combination, it would not contain some vectors that can be formed from those combinations, obviously. So see, this is very intuitive. Okay, how? So see, this line summarizes everything. So if we try to create a smaller space, that would not include all the combinations, and hence that would not span it. So this is exactly the perfect size of the space. So that is the minimal space which we had. So what is basis? For a space is a sequence of vectors with two properties. Basis for a space is a sequence of vectors with two properties. So these are just vectors with two properties. One is that they all span a space. They're independent, so they should be independent. Independent means there should not exist a linear combination of them equating to 0, or they also should span a space, which means all the combinations of them should be included in that space, or that should be minimal also. Space in R3, one basis is for space in R3, one basis is this. So this essentially spans R3 also, because there are three vectors, and they will obviously span. If we take all the linear combinations, it will essentially form the whole three-dimensional space. No combination of these can generate a small null vector, except the 0. So okay, so this is also a condition for independence of these three vectors, that combination should not result in 0 except the 0 vector. If you multiply it with 0, 0 plus 0 plus 0, so yeah. So this is essentially a null space. This is essentially a basis of R3. This space is these three vectors are essentially a basis of R3. That's cool. Okay. Another basis could be this: 1, 1, 2, 2, 6, 5, 3, 2, 8. First thing is, let's check the independence. So for the case R3, I have three vectors which forms a 3 by 3 matrix. Okay, for Rn, if we have n vectors, gives a basis if n cross n matrix is invertible. Essentially, we can see that the summation of 2 does not form this. Okay, that can be calculated how, if they are independent or not. But for Rn, if we have n vectors, give a basis if the n cross n matrix is invertible. That's the point. So in the case of R3, I have three vectors which forms 3 over 3 space. In R3, we have a 3 cross 3 matrix which is forming a basis essentially. For Rn, we have n cross n matrix which is forming a basis, and the matrix should be invertible. For invertible, it should be square matrix essentially. So this should be, for that it should be n cross n. So that is the condition essentially. And because it is invertible, the determinant should not be 0. So there should not be any linear combination. What is the determinant? Determinant is essentially a linear combination of the columns. So the determinant should not be 0, which defines if it is invertible or not. There can be multiple bases, but the thing basis share is the number of vectors in R3. Okay, for let's say R3, we can have multiple bases, but the only thing which these share, they will be different for each case. The only thing which will be shared will be the number of vectors they have. So in R3 they have 3 vectors which will form a basis essentially. Given a space of column, every basis for the space has the same number of vectors. We got this. So this is the dimension of the space. So first we identified basis. Okay, so there are a lot of terms going around in here. So we have not basis. Okay, first we have independence. So independence will be if there are linear combination, not any linear combination should give 0. So the matrix should not be invertible. So we got independence. Then we got the basis which is formed by independence, and the number of vectors being so they should span the space. So independence done, then the spanning is essentially forming all the combinations and putting them in a space. So if both conditions are satisfied, we can declare that matrix as the basis of some column space. Okay, and then if all the bases of that column space, because there will be multiple bases, share one similar property, which is the size of the other vectors, and that is called the dimension of that space. So the calculating dimension requires calculating of bases, which requires calculation of independence and the spans. So this is some kind of column space for R3. R3's column space, only 2 independent vectors here. These can be formed from the linear combinations of these. So these are not independent vectors. So we can essentially see we will have 2 ranks independently, but only 2 vectors, independent vectors. We can see that because the rank is essentially 2. That can be directly seen here, and we have 2 free columns, and hence that only 2 independent vectors. So all the vectors are not independent, so this will never form a basis, because that is the first condition of declaring a matrix as a basis. The column space will only be made by the combination of these 2. Okay, that's the point. There are 2 independent, or they are also independent, hence they are one of the bases. Okay. So the matrix is essentially not a basis, not independent vectors, but for the column space, these 2 vectors span the column space. These 2 vectors span the column space. They are independent. We can calculate by calculating the rank and then the pivot variables, pivot columns. Pivot columns will be essentially independent, and these are independent for sure. And these will also span the column space, because the combination of these 2 will form all other vectors in that column space. Cool. So these 2 vectors form a basis for the column space, not the R3. They are also independent, they will form a basis. Rank of the matrix 2 is number of pivot columns, is the dimension. So dimension is essentially 2, because there are the n is 2 here, which is the rank. So we can find that by intuition, that rank is 2, pivot columns are 2, dimension is 2. Another basis is something like this. So yeah, these are independent in itself. There is no combination which can build a 0 here. If we know that the dimension of the column space is 2, then these 2 independent vectors can't help, but they have to span the space. If we know that the dimension will be 2 for a column space, then they have to span it also. How we can identify that? So for spanning, because the dimension is 2, this is kind of obvious to say that, let's say the dimension is 2. So we have these 2 vectors which will form all the which will be independent, because the dimension is 2, and because the dimension is 2, and these vectors will be independent, hence these vectors will be independent, hence they will form a column space with all the combinations of only these 2, and hence they have to span the space. Because if there is if we introduce another vector and try to span the space, they will never be independent, because the dimension is 2. If we try to introduce another vector to these to span the space, but the dimension is 2, they will never be independent. Dimension of the column space will be R. Okay. Okay. Cool. Where we were? Okay, we have done this. Yeah. So let's talk about n of a then. Telling us the combination of the vectors that give us 0. They are telling us in what way the columns are dependent. So if we have a null space for a for that the basically the null space of that matrix is here, so or of that column space is that. So if that is telling us a combination of vectors that will give us 0, so this is the combination of vectors of that matrix which will give us 0. We know that from this, but they're also telling us in what way the columns are dependent. Intuitively they are also telling us what way the columns are dependent. How? Because the dependence, being dependent, depends on the null space. If there exists a null space except 0, they will be dependent. So this is also depending explaining how, in what way the vectors are dependent. So the first -1 of first column, -1 of second column, 1 of second third column, and 0 fourth column will tell us the dependence of the columns algebraically. Null space consists of all those combinations of these vectors. Null space consists of all those two combinations of these vectors.